Today on the deep dive, we're plunging into something that's, well, often seen as a big step up in calculus, the sophisticated world of techniques of integration. Our guide for this is Chapter 7 of Calculus, Early Transcendentals, the Stewart, Clegg, and Watson text. And our mission really is to break down the key ideas, the formulas and strategies from this pretty dense chapter, giving you a faster path to understanding these really powerful calculus tools. We'll unpack the how and definitely the why.
Exactly. And we're not just listing techniques, right? We want to connect the dots, show how these methods build on what you already know, and crucially, how they open doors for, future applications. The goal is to make these complex ideas feel concrete, graspable, to really equip you with a solid foundation you can actually use.
And that's the core thing, isn't it? Integration, it's not like differentiation where you often have one clear rule. It feels much more like an art. It demands some clever thinking, a whole toolkit, really. And that's exactly what this chapter gives you. Think of it like getting your master set of tools for tackling any integral. We'll even see how these tools can figure out something as wild as rocket fuel calculations. Okay, let's start with the basics, ground ourselves a bit. The chapter kicks off reminding us about the fundamental theorem of calculus. You know, that amazing link between derivatives and integrals. It lets us evaluate definite integrals by finding antiderivatives. And a quick jog of the memory on basic formulas, power rule, 1xx, the usual trig suspects, foundational stuff.
Absolutely foundational. And while the substitution rule, you've probably seen that before, is super important, it's just one tool. The real challenge, and why this chapter is so key, is that there's no single magic bullet like the chain rule for differentiation. Finding the right approach often takes, well, a mix of strategy and sometimes a bit of creativity.
And that rocket fuel example you brought up, it nails this need for ingenuity right away. The source hints at it early on. Figuring out the fuel to get a rocket to a certain height. That takes these integral techniques. So this isn't just theory, right? It's about solving actual engineering problems. Okay, foundations down. First big tool in the box, integration by parts. This is basically the mirror image of the product rule for differentiation.
Exactly right. And the beauty of it is how it takes a tricky product integral, something like x times sin x, and breaks it down. Makes it more manageable. The formula itself, udv equals uv du, it's more than a formula, it's like a strategic plan. You're choosing your u and your dv very deliberately. You want u to get simpler when you differentiate it, right? And dv needs to be something you can actually integrate easily to find v.
Right. So for ex sin x dx, if you pick u epsx, its derivative dx is super simple, perfect. But if you pick u ev dx, well, that gets more complicated, not less. The aim is always to make that new integral, the ev part, simpler than what you started with.
And it's interesting, sometimes you have to apply it more than once on the same problem. Think about something like dt2 dt. You use parts once, and the integral you're left with still needs integration by parts. It can even be used in this clever way to solve for an unknown integral, where the original integral kind of pops back up on the other side of the equation, and suddenly it's just algebra.
And it works just fine for definite integrals too, doesn't it? The formula just gets the evaluation limits added. The source mentions a01 tan 1x dx. Evaluating that gives you a specific area under the curve. It really shows how versatile this method is.
Totally. And for those who like spotting patterns, integration by parts is also the key for deriving what we call reduction formulas. Like for a is sin x dx. These let you relate an integral with power n to 1 with a lower power. Super handy if you're doing these repeatedly.
Okay, next up, trigonometric integrals. This section is all about tackling integrals with powers and products of trig functions, and the trick seems to be using trig identities strategically, like having a secret map.
That's a great way to put it. A secret map, we can sort of break it down. For sines and cosines, if one power is odd. Save one factor, like sin x, convert the rest using sin 2x plus cos 2x equals 1. That sets you up perfectly for a u substitution. But if both powers are even, you have to use the half-angle identities, sin 2x equals 12, 1 cos 2x, and the cosine version. And this directly helps find areas like chloro sin 2x dx, which nicely works out to 2.
So sines and cosines covered. What about secants and tangents? Similar game plan.
Pretty much, yeah. Similar strategies, but based on their derivatives and identities. You're using things like tan 2x is sec 2 by 1, and remembering that the derivative of tan x is sec 2x, and the derivative of sec x is sec x tan x. And yeah, knowing the integrals of tan x and sec x themselves is definitely useful. N ln sec x and ln sec x plus tan x. Oh, and the source also mentions product to some identities, like for sin a cos b. Those can be real time savers for integrals of products with different arguments.
Which leads us neatly into trigonometric substitution. This sounds clever. Like using trig to tame those pesky square roots you sometimes find in integrals. kind of like using geometry for circles or ellipses.
Perfect analogy. That's exactly the idea. You substitute x with a trig function of a new angle, and the goal is to make the square root disappear. There are three main scenarios. If you see a 2 by 2, you go with x equals a sin, because 1 sin 2 is cos 2, see, square root gone. For et 2 plus by 2, you use x equals a tan, because 1 plus tan 2 is sin. And for tangere 2, a2, it's x equals a sec, using sec 1 equals tan 2. That's the magic.
And the right triangle, that's how you get back from a to x at the end, right? Makes it visual.
Crucial step, yep. Especially for indefinite integrals. Got to translate back. But it's worth saying, trig sub is amazing for these specific forms, but don't forget to check for a simple u sub first. Sometimes that's all you need. Always look for the easy win. And oh yeah, if the stuff under the radical is a quadratic that doesn't quite match, completing the square can often reshape it into one of these forms.
Okay, moving on to integration of rational functions by partial fractions. This feels like taking apart a complicated machine, like a polynomial fraction, into simpler pieces to see how it works.
Exactly. It's all about decomposition. But first, a key check. The degree of the polynomial on top must be less than the degree on the bottom. If it's not, you absolutely have to do polynomial long division first. That gives you a polynomial part easy to integrate, plus a proper rational function where the top degree is smaller. That's what you decompose.
Right. And then the cool part, you factor the denominator completely, break it down into linear factors like xa and irreducible quadratic factors like by 2 plus b, and then express the whole fraction as a sum of simpler partial fractions based on those factors.
Precisely. And there are rules for what form each partial fraction takes, depending on the factor type: distinct linear, repeated linear, irreducible quadratic, repeated irreducible quadratic. It sounds complicated maybe, but it's systematic. And the beauty is, once you've broken it down, those simple pieces are usually integrable using basic logs or inverse tangents. It turns something that looked impossible into just, well, several manageable steps.
So after all these specific methods, we hit strategy for integration. And this feels like where the art part really comes in. Like you said, no single flowchart, more like needing good intuition.
Spot on. No magic algorithm. But there is a practical strategy, a kind of mental checklist. Step 1, simplify. Always. Algebra, trig identities, anything to make it look nicer. Step 2, look for an obvious substitution. Is there clear u and do's staring at you? Try that first. Step 3, if not, classify the integrand. What kind of function is it? Trig, rational. A product suggesting parts. Does it have those specific radicals for trig sub? Basically, try to fit it into one of the boxes we've just discussed.
And if none of that works, what's step 4?
Step 4 is try again. Get creative. Maybe a less obvious substitution. Different manipulation. Combine methods. It really drives home that integration can sometimes be a puzzle needing patience.
Which leads to this really interesting, almost philosophical point. Can we actually integrate every continuous function using these elementary techniques?
And the answer, maybe surprisingly, is no. It's a really deep insight. Even with this powerful toolkit, lots of seemingly simple functions just don't have antiderivatives that we can write down using elementary functions. You know, functions built from polynomials, exponentials, logs, trig functions, and roots. The integral exists as an area, sure, but you can't write down a formula for it using those basic building blocks. Famous examples are e by 2 dx, super important in statistics, or ln by 2 dx, or 1 ln x dx. It's humbling, shows the limits of these methods.
Okay, so given that limitation and just the general complexity, integration center using tables and technology makes a lot of sense.
Yeah.
Using pre-made integral tables or computer algebra systems, CAS. Smart tools?
Yeah, tables are handy references. But often, you still need to massage your integral a bit, maybe do a substitution to make it match the exact form in the table. It's not always plug and play.
And CAS. Those software tools are amazing at pattern matching, right? They can crunch through integrals incredibly fast. But there are catches, aren't there? Like they might forget the plus C or absolute values in logs, or give an answer that's technically right, but maybe not the simplest or most useful form.
That's exactly the point. The human element is still crucial. You need to understand the calculus to know if the CAS output makes sense, if it's missing something, or if you can simplify it further. It's definitely a collaboration, human insight guiding the machine, not just blindly trusting the output.
Right. So sometimes finding an exact answer is impossible, like
Yeah.
with e by 2 dx, or maybe you don't even have a function, just data points from an experiment. That's where approximate integration comes in.
Exactly. When exactness is off the table, we estimate. We can think back to basic Riemann sums, left or right rectangles. But for better accuracy, we use methods like the Midpoint Rule. using the midpoint of each interval for the rectangle height. Often gives a better balance. Then there's the trapezoidal rule, which averages the left and right endpoints, essentially drawing trapezoids. And arguably the most accurate for this level, Simpson's rule. It uses parabolas to hug the curve more closely. Needs an even number of intervals, though.
And each one has error bounds, right? Ways to estimate how far off the approximation might be. With Simpson's rule usually being the most accurate for the same number of intervals, its error shrinks faster.
Generally, yes. Simpson's rule converges quite quickly for well-behaved functions, and this is super practical for real-world data. Estimating total network traffic from periodic readings, average daily temperature from hourly measurements. These approximation rules let you get meaningful numbers from discrete data points, which is huge in science and engineering.
Okay, last section. Improper integrals. This sounds like pushing integration to its limits, dealing with infinite intervals or places where the function blows up.
That's exactly it. Stretching the idea of a definite integral. Two main types. Type 1 is integration over an infinite interval, like fx dx ax. You handle this by taking a limit. You integrate from 1 to, say, t, and then see what happens as t goes to infinity. If the limit is a finite number, we say it converges. If it goes to infinity or doesn't exist, it diverges.
And this gives that really cool counterintuitive result. 1 by 2 dx converges, finite area, but a 1x dx diverges, infinite area. Even though the functions look kind of similar way out there, it's all about how fast they drop towards 0. Like 1 by 2 just drops faster.
Precisely. And that leads directly to the very useful p-test for Apro-Kirchhoff or 1x pdx. Converges if p1, diverges if p1. A fantastic shortcut. Then type 2 is when the function itself has an infinite discontinuity, a vertical asymptote within the interval you're integrating over. Again, you use limits. You approach the point of discontinuity carefully from one side to the other.
Which brings up that critical warning. You have to spot these. Trying to just plug in the limits for something like A03 1 by 1 dx will give you nonsense because of the asymptote at x1. You have to split it at the discontinuity and use limits.
Absolutely essential. Gotta split it. And sometimes you can't easily find the value of an improper integral, but you want to know if it converges or diverges. That's where the comparison test comes in. If you can compare your tricky integral to a simply one you know converges or diverges, you can often figure out its behavior. The classic a by 2 dx is a great example. We know it converges, even though we can't write down its antiderivative easily. Its value, interestingly, turns out to be AC2, usually shown using multivariable calculus tricks.
Wow. So improper integrals are key in things like probability, some physics problems, population models, places where things might go on forever or have sharp spikes. Okay, what a tour. From the basic building blocks to, well, the edges of infinity and the limits of integration itself, we've really built up a serious toolkit today. Parts, trig integrals, trig sub, partial fractions, and strategies for choosing the right one. It's definitely a mix of knowing the rules and having that creative spark.
That really sums it up. Integration is a journey. It's not always step-by-step obvious. It forces you to think critically, to check assumptions, and just appreciate the subtleties. Even realizing that not everything can be integrated easily tells you something important about math itself. It's still evolving.
Yeah, it's way more than just crunching numbers. Getting good at this stuff gives you a deeper way to understand the world. From, a rocket's path to how data flows, it's analytical thinking that applies everywhere. So now, as we finish up, maybe a final thought to chew on. If most everyday functions don't have simple, elementary antiderivatives, what does that suggest about the huge universe of functions out there we haven't even fully explored? Makes you think about the ongoing quest to understand it all, doesn't it? Well, thank you for joining us on this deep dive into calculus techniques. The team here at Last Minute Lecture really hopes this was helpful. Until next time, keep exploring.